Happy Friday. And we have a great speaker today from straight from the Center of Coastal and Ocean Mapping, Dr. Yuri Rzhanov. He received his PhD degree in semiconductor physics from the Russian Academy of Sciences in 1983. Before joining us here at UNH in 2000, he was working at the Heriot-Watt University of Edinburgh, Scotland. His research interests include optical methods of seafloor mapping, bone structure reconstruction with multiple views, time-of-flight cameras, shallow bathymetry detection using lidar and/or satellite data. And currently, he's a research professor here at CCOM-JHC, straight at the University of New Hampshire. So everyone, please introduce Dr. Yuri Rzhanov.
Today I'm going to talk about the data, what can be extracted from the data obtained from ICESat-2 satellite. Some heard about it, some haven't, and I'm not going to go into many details. I'll just stop at the moments which are specific to our particular interest here. But if anybody has questions, we can always return back to the numbers I'm going to present now, and I'll explain in a little bit more detail, although I'm not sure that I know sufficient amount of detail about it. So this satellite is about 7 years old, and it has been designed to work with ice and snow, and for that it is equipped with green laser, which reflects from reflecting surfaces, gets back to the satellite, and we get some information about ice and snow. For us, what is important is that this green laser can penetrate water when it's not very deep. And also, the reflection comes back to the satellite, and we get some information about it. So, that's how it looks like. It sends 6 tracks, 3 strong and 3 weak. They are about like 4 times weaker than strong ones. And it sends a lot of pulses per second and a lot of photons per pulse. Like trillions. That reminds me of the Nation Dead. I don't remember trillions in other situations. So, green light penetrates water, it refracts a little bit there, and out of all these trillions, we get back only like 10, 15 at most returned georeferenced photons. So this is an event, and that's why it's called photon event. And that's what we are dealing with when we are processing data. So there are pros and cons as usual. There are positive sides of the data that we are getting from ICESat-2, and there are negative sides. So we'll concentrate on the positive sides because negative not very productive. So there are lots of products that can be extracted from the data. So this is what telemetry gets, and these are all products that can be produced from this raw data. And soon we'll have product ATL24, which is directly related to shallow bathymetry. It's obtained from ATL3, this part. And but this product is not going to be just the way to get bathymetry. It's more of a set of recipes that can be applied in certain circumstances. That's my understanding, at least. So our attempt was to add another recipe for extraction of bathymetry from ICESat data. So the proposed algorithm is fairly simple, and it's based on two important things: density and structure of these photon events. So density is clear because if we have 1, 2, 3 photon events, it means nothing. There must be many photons. And second, they have to be arranged in certain structure, because if they are scattered chaotically, doesn't mean anything again. So they have to be organized in a certain way. So this is everything, basically everything that we know how to extract data bathymetry from this data. So this is a typical track with bathymetry. So this is a long track. So for each point we know easting, northing, latitude, longitude, etc., etc. And this is height. So I like the term height rather than depth, because height is positive and negative, and depth is positive and negative depth range. Okay, so I like to use height. And that's a pretty good, actually, track, because this is obviously water surface. This is obviously bathymetry, because it's below zero. And we may even conclude that this bathymetry gets to the surface, and because something is being built here that has clear structure. That's what normal human expert would say, looking at this structure. So, what our algorithm consists of? We take the single photon event, and around it we draw several ellipses, and also dissect in sectors. In this case, n sectors and 3 ellipses. And then, so we end up with cells of some funny shape. And then we calculate number of other photon events that happen to be in this cell. So for example, in this cell, there's just 1. In this cell, there are 3. So we calculate, count all these, and end up with a vector, where each element of the vector is an integer corresponding to a number of other photon events happen to be in certain cell. And of course, we have to add height of this photon event, and this is very important because without it, you remember, water surface would be a perfect candidate for bathymetry. It's very dense, it has distinct structure, so we have to separate somehow from this situation. So we end up, for each photon event, we end up with this long vector. In this particular case, it's 3 ellipses and sectors plus 1. So the data sets we are dealing with here, we worked with, was Key West, Florida, just because we happened to have it already, and we worked with it. And second, we chose the number of places around the globe which were selected by these guys in their paper, which also proposes a certain recipe to extract bathymetry. So we thought, if they can use these trucks from these areas, coastal areas, then why not us? So these are 2 data sets we were working with. And then we downloaded all this data and prepared it in the following way. So first of all, we assumed the role of the expert. We decided that we are qualified to decide what is bathymetry and what isn't. divided into smaller chunks because it's easier to deal with them, manually marked photon events that are bathymetry from our point of view, and for each photon event, every photon event, not just those that we marked, but for all of them, calculated vectors the way as I explained. So as a learning machine, we used light GBM. We could have used other things like head boost, random forest, but we thought, why not light GBM? It's relatively new, and it's been developed by a relatively respectable company, so why not? So the mode of training, as many of you already know, happens according to the following scenario. So we have a data. So all these vectors are here. These vectors are divided into two parts. Larger part, typically larger, which is a training part, and testing part. So using light GBM, we train a model based on this training set. And then we applied this model to testing part. And as we know here, ground truth, which we decided is ground truth, and we have model's prediction, we get some accuracy. And for binary classification, bathymetry or not bathymetry, we get accuracy about 0.98%. So, well, 0.98 or 98%. So the most interesting thing, of course, here is the F1 score, because it's a harmonic combination of precision and recall. So that's a quite popular metric in classification. So, and 98% is pretty good result. So, and every time we do classification, we end up with something which is called confusion matrix. What is confusion matrix? It has diagonal elements where the prediction of the model coincides with the decision of an expert, of the ground truth. And off-diagonal terms, which are events when we disagree. We think one thing and the model says, no, you're wrong. So the larger the diagonal terms, the better. The smaller the off-diagonal terms, again, the better. So the question arises, where this came from? How come they are? How come they do exist? Why there are not zeros? And so for that, we chose a piece of reasonably flat bathymetry, applied the model to it, and then built vertical histogram. Here it is. So green is true positive. So when we agree with the model that this is bathymetry.